Today we are walking through the paper, titled Looped World Models.
What problem is this paper trying to solve first?
The paper starts from attention in world models. To simulate far into the future, the model needs deep computation. But making the model deeper usually means more parameters, higher deployment costs, and more chances for small prediction errors to compound over a long rollout. Looped architectures already tried to separate computation depth from parameter count in language models by reusing the same transformer blocks several times. The gap here is that this idea had not been worked out for world modeling, where the model must predict latent states, rewards, and whether an episode continues.
So the word looped means the same block is used repeatedly, not that the model simply gets larger.
Exactly. Looped WM keeps a shared transformer dynamic score and runs it for multiple inner iterations. That gives the model more thinking steps for a transition, while the number of learned parameters stays much closer to a smaller model. This architecture picture is the best entry point. On the left, the model takes an observation and an action. The observation encoder makes a latent vector. The action embedder maps the control signal into the same space, and the previous latent state can also be fed back.
Where does the repeated computation happen in this diagram?
It happens in the central loop dynamic score. A prelude block forms a conditioning signal. Then a shared recurrent transformer block refines the hidden state for loop steps 1 through t, and the coda turns that refined state into the next latent state. The important engineering choice is that the loop is spectrally stabilized. In plain terms, the recurrent part is constrained so repeated latent updates do not blow up as the rollout gets longer.
What does the stability equation actually enforce?
The paper defines A as a diagonal matrix with negative entries made from -exp of a learnable vector. After discretization, A bar becomes exp of delta times A, so its diagonal entries land between 0 and 1. That is why repeated state retention is damped instead of explosive. There is also an adaptive early exit. During inference, a small gate checks the current loop state. If the transition looks settled, the model can stop early. If the transition is harder, it can spend more loop iterations up to the chosen maximum.
That handles one transition. How does the model avoid decoding every intermediate future state?
That is the deferred decoding part at the bottom of the figure. Instead of decoding an observation after every action step, the model can roll forward through latent states and decode only the final state. The paper adds terminal prediction and latent trajectory constraints so the hidden states stay meaningful even without intermediate reconstruction. The paper frames deferred decoding as a nested loop. The outer loop moves through actions over a horizon k. Inside each action step, the shared transformer block refines the latent state over t inner iterations, so computation is spent in latent space before the expensive observation decoder is called.
What evidence do they show for parameter efficiency?
The right side of the architecture figure plots prediction quality against model scale. The loop WM curve is above the baseline world model curve at comparable scales, and the highlighted point reports up to 100 times parameter efficiency. The claim is not just that bigger is better, but that repeated latent computation gives more useful depth per parameter. The same figure also shows the long horizon stability story. The baseline world model's error curve rises as rollout horizon grows, while the looped model stays much lower. That matches the design goal of spectrally stabilized latent dynamics plus deferred decoding.
Do the external test results point in the same direction?
Yes. In the online performance chart, the bars compare relative increase over Q1. The baseline vision language model improves next-day retention by 38.4%, while LWM improves it by 122%. For monthly retention, the baseline reaches 86.1%, while LWM reaches 232.4%.
Which comparison matters most in that chart?
The key comparison is LWM against the baseline VLM, not just LWM against Q1. LWM is about 3 times the baseline gain for next-day retention, and more than 2.5 times the baseline gain for monthly retention. That supports the idea that latent rollout structure helps when user behavior has to be predicted across time. The human evaluation chart checks quality more directly. Against the baseline VLM, LWM scores higher on appropriateness, informativeness, engagingness, and human likeness.
Are the gains broad or only on one human score?
They are broad in this evaluation. LWM rises from 56 to 91 on appropriateness, from 70 to 93 on informativeness, from 81 to 90 on engagingness, and from 65 to 86 on human likeness. The largest gaps are in appropriateness and human likeness. The deferred decoding analysis adds a more specific takeaway. The paper reports that deferred decoding is useful, and that its usefulness tends to grow when rollouts are accumulated. That fits the architecture. The model is rewarded for keeping latent trajectories useful over multiple action condition steps.
What limitations should we keep in mind while reading the results?
The manuscript says its disclosure is intentionally selective. It establishes the architectural thesis, but broader cross-family comparisons, richer scaling analysis, and more optimization details are left for future disclosure. So the strongest takeaway is the design case, not a complete final benchmark map.
Then what is the final message of the paper?
The final message is that world models can gain useful depth by looping in latent space instead of only scaling parameter count. Loop WM combines a shared recurrent transformer core, spectral stability, adaptive loop depth, and deferred decoding, then backs that package with retention and human evaluation gains over baselines. That wraps up this paper walkthrough.